forgot to answer question number 11 on side 1. So we'll take care of that. The slope of a position versus time graph represents the velocity of the object. If it's straight line, average velocity. If it's along the curve, the slope of the tangent line would represent an instantaneous velocity at any clock reading along the way. Moving on to side 2. It says, assume the velocity versus time graph to the right is for a ball rolling down a ramp with a starting velocity of 0 meters per second. Show your work when calculations are required, including general equations. So we have a velocity versus time graph. It looks like the starting velocity is 0, and at 5 seconds, the velocity is 20 meters per second. So we can just plop that down. What's the velocity at 5 seconds? What's the slope of the graph with units? In this case, we should show calculations. We know that the slope is the change in velocity divided by the change in time. Our total change in velocity is a positive 20 meters per second divided by 5 seconds. 20 divided by 5 is 4 meters per second per second. So that's meters per second squared, or 4 meters per second per second. Next up, what's the specific meaning for the slope? It would mean that for every 1 second, something is changing by 4 meters per second. What do we measure in meters per second? Velocity. So for every second, the velocity increases by 4 meters per second. As we continue along through this, what's the physical significance of the slope? In other words, what does the slope of any velocity versus time graph represent? Well, it tells us the rate at which velocity changes with respect to time, and acceleration is what we use to describe how velocity changes. And moving on, let's see here. Try to scroll this up and scroll this down. What would the velocity be at 10 seconds? To do that, we are going to have to do some calculations. We know that velocity is equal to the acceleration times the time. We don't need the y-intercept, so the starting velocity was 0. So our acceleration we had calculated just a little bit ago is 4 meters per second squared. We plug in 10 seconds for the clock reading, and 4 times 10 is 40 meters per second. So that would be the velocity at 10 seconds. Now if we compare those two, at 5 seconds, the velocity was 20 meters per second. At 10 seconds, the velocity was 40 meters per second. So what happened to the velocity when we doubled the time? Well, the velocity doubled as well. Time doubled from 5 to 10, the velocity doubled from 20 to 40. As we continue, we'd bust on to letter G. It says use a graphical representation to find the displacement for the first 5 seconds. Now we know that the area under a velocity versus time graph is the displacement. Now this area happens to be a triangle. So we know the area of a triangle is 1/2 the height times the base. All right, in this case, that means our displacement is going to be 1/2 the height of this triangle is our final velocity, or the velocity at 5 seconds. Our base is going to be our change in time. So we got 1/2 times 20 meters per second times our base of 5 seconds. We know half of 20 is 10, 10 times 5 is 50. And meters per second times seconds, meters per second times seconds. The seconds cancel out, leaving us with just meters. Letter H asks us what would the displacement be at 10 seconds, and they want us to use a mathematical representation. It says here displacement is 1/2 the acceleration times the change in time squared plus the initial velocity times the change in time. But in our case, our initial velocity is 0, so we don't really need that portion of the equation. So we got displacement is equal to 1/2 the acceleration times the change in time squared, and we're doing this for 10 seconds. So we got 1/2 the acceleration was 4 meters per second squared times 10 seconds, but that has to be squared. Well, what is 10 seconds times 10 seconds? Well, that would be 100 seconds squared. We know that half of 4 is 2. 2 times 100 is 200 meters per second squared times seconds squared. The seconds squared cancel out and leave us with just meters. So our answer is meters. In the next question, it asks, as we doubled the time, the velocity doubled, but as we doubled the time, what happened to the displacement? Well, again, our clock readings, well, I guess it's a when we displacement from 0 to 5 was 50 meters, but the displacement from 0 to 10 was 200 meters. How much bigger is 200 meters compared to 50 meters? Well, it's 4 times bigger. It quadrupled. Why does that work? Let's take a look at a velocity versus time graph. So the graph we have sketched up earlier has a portion of this graph on it. They said at 5 seconds, the velocity was 20 meters per second. When we double the clock reading to 10, the corresponding velocity doubled to 40. But when we take a look at the displacement, that's the area under the triangle, or under the curve. So we have a triangle that's that big, and that triangle happened to have a representation of 50 meters. Right? This was 50 meters was the area of that triangle. Well, when we look at the displacement from 0 to 5 to 0 to 10, we could break it into smaller triangles like this. Well, how many triangles do we have when we went from 0 to 5? Well, we had our first triangle and a second, and each of these is worth 50 meters, and a third and a fourth, each of those being 50 meters, which is why the displacement quadruples when we double the time. I hope that helps.